So this is the Waves Homework Booklet, question 11. So we've got a note being played on a violin. And when that happens, it's produced actually of the first and many other harmonics. Figure 1 shows the shape of the string for the stationary wave that corresponds to one of the harmonics. The positions of maximum and zero displacement for one harmonic are shown. Points A and B are fixed, so A and B are the fixed ends, X, Y and Z are points on the string. Describe the motion of point X. So point X is here, and just like all the other points on the stationary wave, it's simply going to oscillate about the equilibrium position. It's going to oscillate, there's the equilibrium position, and it's going to oscillate either side of that. I say it's the same true of every other point. There are obviously points that don't. Those are the nodes which simply don't move. There is another way you can state that, which is to say that it vibrates instead of oscillates, and you could say that it's perpendicular to the central line instead of about the equilibrium position. Now, slightly tricky is the phase relationship between a couple of places. So we've got the phase relationship between X and Y. Now, you need to start thinking here. We've got half wavelengths. If we include the antinodes, we're splitting that down into quarter wavelengths, and X is halfway between 1/4 of a wavelength and 1/2. So it's actually 3/8 of the way into the cycle. And Y is another 3/8 further on. So X and Y are 3/8 of a cycle apart, 3/8 of a wavelength apart, if you like, on that diagram. Now the phase relationship is 2 pi, because a complete cycle is 2 pi lots of that. So what we've got 3/8 of a cycle, so it's 2 pi times 3/8. That's 3 pi by 4, 3/4 pi radians. Now if you want to do that in degrees, that's 135 degrees. X and Z are very nearly a whole cycle apart, but they're actually 1/8 of a cycle off that. They're 7/8 of a cycle apart. So again, 2 pi radians for a whole cycle, so we need to take the 7/8, multiply that by 2 pi, and I get 7 pi by 4 radians. You could very well express that as 1 3/4 pi radians, and the other thing that's interesting there is I could, because Z is in phase with that point there, I could well also think of that as simply 1/8 of a cycle difference, so it's also pi by 4. 315 degrees, 45 degrees if you want to express it in terms of degrees. We're given the frequency of the harmonic, show the speed is 125. Now that word show is very, very important, because it means that I can't just give the answer, I have to explain what's going on as well. If I look back at the diagram, I can see very quickly that one wavelength, it would be from there to there. There's another wavelength from that midpoint to the end. So my 320 mils is two wavelengths, so one wavelength is 160 mils, and that means that one wavelength is simply 0.16 meters. I have no idea what mn means. Let me just get rid of that. There we go, and let's see if I can draw that away. Nearly gone. Excellent. Okay, so 0.16 meters. C equals F lambda, 780 times 0.16, 124.8. Now that's too many significant figures, but because it's a show question, it's a really good idea to do that, to give too many significant figures, because it proves that you've actually done it. So the show part of that, I've given my formula, I've written out the equation, and then I've given my answer to too many significant figures. It's not really the too many that matters, but it's more significant than the number I've been asked to show it's equal to, or is about. Finally then, calculate the time, no it's not finally, the time taken for the string at Z to move from maximum displacement back to 0. So if we zoom all the way back to the diagram, here's Z, and one cycle would look like that, from the top to the middle, middle to bottom, bottom to middle, and middle back to the top. So Z going from maximum back to the middle is 1/4 of a cycle. Well, one cycle takes the time of one period. We've got the frequency, so therefore I can work out the period. The period is 1 upon the frequency, is that value. So the time I want is a quarter of that, dividing by 4 gives me that amount of time. Key there is, hopefully you recognise that you need the period because I want a quarter of it. How can I work out the period? I've got frequency, therefore I can work out period. Now the violin presses on the string at C to shorten the part of the string that vibrates. So between A and C is now not vibrating. Figure 2 shows the string between C and B vibrating on its first harmonic. The length of the string is 320 mil, and the distance between C and B is 240 mils. So the key thing here is that that number is not relevant. What matters is the length of the string that's actually in use, which is the 240 mils. State the name of given to the point on the wave midway between C and B, so that's where I'm going to have maximum displacement when I've got the first harmonic, so that is an antinode. Calculate the wavelength. Remember, from node to node, which is 240 mils, is half a wavelength, so I've written that into meters, 0.240, and therefore the wavelength is twice that, 480 millimeters. And then finally calculate the frequency of the first harmonic, and the key is it's the same string. It might be shorter, but it's the same mass per unit length, it's the same tension, so the speed of the progressive wave remains at 125 meters per second. C equals f lambda. Rearrange that, dividing each side by lambda. F is C over lambda, therefore I've got the wave speed. I'm going to use the full value I calculated, 124.8 divided by 0.480, and that works out as 260 hertz. So that's the Waves homework booklet, question 11.